Welcome to the PMDG 777-200LR Air Conditioning and Pressurization Groundwork lesson from Angle of Attack. Today, we're going to run through the important aspects of the air conditioning and pressurization systems aboard the 777. This lesson will be divided into two main areas. On one hand, we'll look at all the intricacies of the fundamental air conditioning system. On the other hand, we'll talk about how the 777 maintains its cabin pressurized to a comfortable level so that your FS passengers can breathe normally and not freeze when flying at 20 or 30,000 feet. Here's the list of topics we're going to discuss: air conditioning system introduction, air distribution and temperature control, air conditioning packs, cabin pressure control, typical pressurization profile, outflow valves, and cockpit indications. There are several small portions of the air conditioning system that will only explain at a basic level, such as the ventilation system, Gasper fans, and electronic equipment fans. We encourage you to grab a PMDG 777 manual and read through those paragraphs. You'll surely enjoy it. The 777 air conditioning system controls the interior environment of the aircraft for flight crew, passengers, and equipment. These are the system's three primary functions: control the flight deck and passenger cabin temperature, control fresh airflow for cabin pressurization and ventilation, and recirculate cabin air for ventilation. Two main components create the supply of fresh, conditioned air. These are known as the left and right air conditioning packs. We'll simply be referring to them as packs during this lesson. Did you know that the word pack actually stands for pressurization and air conditioning kit? The entire pack process involves cooling, heating, cleaning, filtering, and metering the amount of air that goes into the cabin. Packs work with bleed air supplied from the aircraft's pneumatic system, and as we know from the 777 bleed air groundwork lesson, bleed air is mainly obtained from the high-pressure compressor stages of the engines. Therefore, it's probably not clean or cool enough to be delivered raw to the passengers. Obviously, packs and their air cooling and cleaning process impose a large air demand over the pneumatic system. Therefore, recirculation fans in the passenger cabin help to minimize pack workload by taking cabin air, running it through cleaning filters, and then pumping it back into the cabin. Conditioned air is not only provided by the air conditioning packs. Ground-supplied pre-conditioned air may also be fed into the aircraft through a series of ports in the lower fuselage. Air from all the sources flows into a common pool known as the mix manifold. From the mix manifold, air supplied to the aircraft is metered and controlled according to the demand for cool air by the aircraft's cabin sections. For distribution and temperature control purposes, the aircraft is divided into the following zones: flight deck and 6 passenger cabin zones named A through F. The flight deck receives 100% fresh conditioned air from the left pack. The cabin zones receive conditioned air from both packs, but also a share of recirculated air to minimize the pack workload. As we mentioned before, the recirculation process involves drawing air from the cabin, running it through a series of physical and chemical filters, mixing it with pack air, and then reinserting it back into the distribution ducts. As far as zone temperature control is concerned, here's an interesting point. Both the flight deck and passenger cabins have temperature selectors located in the overhead air conditioning panel. These have automatic temperature control logics that work in the following way. There is one selector for the flight deck and one selector for the 6 passenger cabins. The air conditioning packs are commanded to produce air according to the coldest of all temperature zones. Why does it do that? Because rather than packs producing air with different temperatures for each cabin zone, it's more efficient to have the packs produce air of a single temperature in the mix manifold according to the coldest cabin zone, and then add warm air to all the other cabin zones that require air with a higher temperature. This warm air that's added to pack air is known as trim air. Trim air is bleed air taken from the aircraft's pneumatic manifold. Remember that it does not flow into the mix manifold. Instead, it's mixed with pack air downstream of the mix manifold. Cabin temperature controllers use trim air modulating valves to adjust the temperature in cabin zones that need more heat. Trim air from the left engine bleed system works with the flight deck, 3 passenger cabin zones, and the aft cargo compartment. Trim air from the right engine bleed instead is added to the 3 other passenger cabin zones, forward cargo compartment, and the electronic equipment compartments. Trim air switches in the overhead panel command the operation of trim air modulating valves. The trim air switches have the following positions. On. Trim air modulating valves are commanded open and regulated by the cabin temperature controllers. Off, with on not visible. Trim air valves are commanded closed and the fault light illuminates. Whenever the fault light illuminates, it's a signal of a problem with the trim air valves. This could be triggered by trim air valves failing closed, a zone supply duct overheat, or simply if the related trim switch is selected off. Referring back to the temperature selectors, the first is the flight deck temp selector, and it has the following positions. Auto provides automatic temperature control for the flight deck, maintaining an average temperature of 24 degrees Celsius. Manual provides manual control of the trim air modulating valve. Turning the valve from the manual position to the C detent drives the flight deck zone trim air modulating valve to closed, so air from the mixed manifold is higher in proportion to trim air. Similarly, turning the valve from the manual position to the W detent drives the flight deck zone trim air modulating valve to open, so there's a higher amount of trim air flowing into the flight deck. The temperature limits during automatic and manual operation are 18 degrees Celsius and 29 degrees Celsius. The cabin temp selector works in the same way, but has a more automatic logic than the flight deck temp selector. The cabin temp selector provides automatic temperature control, with the normal master reference temperature being 24 degrees Celsius. Turning the knob towards C or W changes the master reference temperature between 18 degrees Celsius and 29 degrees Celsius. If either temperature selection is impossible to achieve by the pack temperature controller because of system fault, the pack outlet temperature is regulated to achieve the last commanded temperature, or an average temperature of 24 degrees Celsius. For the cabin sections at least, there are auto comfort correction features that automatically compensate for temperature changes during different flight phases. For example, a cruise condition would cause the cabin temperature controllers, which we'll now refer to as CTCs, to adjust the cabin temperature up to ensure that the cabin stays at a comfortable temperature when the aircraft's skin is exposed to about -50 degrees Celsius at high altitudes. The last bit of the distribution system has to do with ventilation. The ventilation system removes odors from lavatories and galleys, causes airflow across the different temperature sensors in the flight, passenger, and cargo compartments, and supplies airflow into the bulk cargo compartment. Now, that's as far as we're going to take it in terms of air distribution and temperature control. We've mentioned the word pack a lot during this lesson, and it's now time to have a specific look at what packs are and how they operate. The word pack, as we mentioned earlier, stands for Pressurization and Air Conditioning Kit. The 777 has 2 identical packs that essentially provide the housing for all the cleaning, filtering, and cooling of the ram air that is conditioned to enter the cabin. Packs discharge air at a value that is sufficient to maintain the flight deck, passenger cabin, and cargo areas to their automatically or manually commanded temperatures. 2 redundant channels in 2 separate controllers control each of both packs. If one channel in a controller fails, a system logic commands the other channel to assume command immediately. And so we have bleed air. But what exactly happens to it when it goes through either pack? The airflow control system includes the following items in the packs, in the following sequence. Primary heat exchanger, air cycle machine or ACM compressor, secondary heat exchanger, water collector, reheater, ACM turbine 1, condenser, ACM turbine 2, check valve, and mixed manifold. Air from the packs is mixed with recirculated air in the mixed manifold. This air moves through the air ducting system to the passenger zones. The flight deck receives air directly from the left pack. So first, bleed air from the pneumatic system is run through a primary heat exchanger, where it's put into contact with ram air in order to lower the bleed air's temperature. A quick refresh. Remember that bleed air is very hot, highly pressurized compressed air that's extracted from the high-pressure compressor stages of the engines in order to feed the aircraft with pneumatic power. After the first stage of heat exchange, air flows into the ACM compressor stage. The compressor stage compresses air from the primary heat exchanger to increase its pressure. In the process, heat is also produced. Therefore, the air's temperature increases once again. Because of this, and after air has passed through the ACM compressor, it passes through a secondary heat exchanger where again it's put into contact with ram air. Air is then ducted into the condenser and reheater stage. In here is where air flows over both heat exchange cores so that they absorb heat from the air. This temperature decrease induces condensation of moisture in the air into water, so that then a water collector can remove it from the air. During the reheater stage, air is heated once again to add thermal energy to it so that it can later be converted to mechanical energy to operate the turbines in the ACM. The energy that is released in the turbines turns the shaft of the air cycle machine. Finally, downstream of all the components we just mentioned is a check valve. The check valve controls the direction of the flow from the packs into the mixed manifold and prevents backward flow. Okay, let's talk a bit about the actual operation of packs, which is a more important concern at this stage of your 777 training. There are two pack switches, left and right. The switch is a push button that has the following positions. Auto. The pack is automatically controlled by the system. Off. The pack flow control valves are commanded closed, denying the flow of bleed air through them. Whenever the off light illuminates in amber, it's a signal of some form of fault in the related pack. This could be the pack valves are failed closed. An over-temperature condition may have occurred downstream of the compressor or the pack itself. Duct temperature transmitters aid in determining the air's temperature and relaying them to the computers that need the information. Bleed air pressure is inadequate to commence flowing through the airflow control system. The related pack switch is pushed off. Or finally, the right pack valve is closed during an APU to pack takeoff procedure. For more information on this, check out the 777 Groundwork Bleed Air lesson. The detection of these faults, overheat protection, and pack control in general are all automatic processes that do not require significant crew input. Furthermore, in any over-temperature condition or significant pack fault, the system commands an immediate shutdown of the related pack. In this situation, the flight crew can attempt to restore pack operation by pressing the air condition reset switch. Pushing it resets any closed pack flow control or trim air valves that have been held closed due to any of the fault conditions we mentioned before, and also resets fault protection. If there is any fault in the recirculation fans, the air condition reset switch can also restart them. The air conditioning packs also protect themselves from faults whenever there are certain system malfunctions. Pack control in this case automatically enters a standby cooling mode in order to back up normal mode, instead of fully shutting off. If one pack is normal and the other is in standby cooling mode, the standby mode pack shuts off at lower altitude where outside air temperature is not as cold, so as to be uncomfortable for passengers and crew. The important bit to emphasize is that if both packs are in standby cooling mode, or if one pack is inoperative for any reason, the remaining pack can adequately maintain the cabin pressurized. The cabin temperature will probably not be maintained as comfortably as during normal operation, but for sure the cabin will stay pressurized. In fact, during standby cooling mode, because of the lower cooling capacity, temperatures in the flight deck or cabin may be slightly higher at low altitudes or when outside air temperature is high. Speaking about cabin pressurization, let's now move on to the other main portion of this lesson, pressurization. As you may remember from your meteorology manual or from old high school lessons, the atmosphere is made up of air. In the tropospheric region of the atmosphere, the volume of air decreases at a nearly constant rate as altitude increases. They are inversely proportional because air density becomes thinner as we climb. Above the troposphere, there is the stratosphere, which is where most airliners fly due to the relatively calm air and cold temperatures. Unfortunately, in the lower stratospheric region between 30,000 and 40,000 feet, the amount of ambient air makes it tough for humans to survive without being exposed to the risks of hypoxia and other hazards. Hypoxia is an oxygen deficiency condition that presents symptoms only after a period of time since the supply of oxygen has been detained. Just to clarify, this does not happen only between 30 and 40,000 feet, but can happen during any phase of flight. This is particularly dangerous for the flight crew, as it may lead to a pilot incapacitation. There is no emergency worse than a pilot incapable of safely operating his aircraft. For this reason, the 777's cabin must be pressurized so that an adequate and constant supply of breathable air is provided to the flight crew, passengers, and/or any pets you may have chosen to carry in your FS flights. From the earlier section of this lesson, we saw that normally, the air conditioning packs would supply conditioned air into the flight deck and passenger cabin. Regulating the discharge of air from the aircraft overboard controls cabin pressure throughout the aircraft's operating altitude envelope, between 2,000 and 43,100 feet. Air Supply Cabin Pressure Controllers, or ASCPCs, control this discharge of air from the aircraft by modulating between open and closed a pair of valves in the lower fuselage. These valves are called outflow valves, and the 777 has one forward and one aft outflow valve. Here are two concepts you should become familiar with: cabin altitude and pressure differential. Cabin altitude is the altitude at which the aircraft pressurizes its cabin to. The aircraft may be flying as high as FL 400, but cabin altitude may only be 8,000 feet. This means that cabin air is pressurized to a level similar that you may encounter at 8,000 feet under ISA conditions. It may sound like a simple clarification, but keep in mind that as altitude increases, ambient pressure decreases. Therefore, as cabin altitude increases, cabin pressure decreases. And so, the difference between cabin pressure and outside ambient pressure when the aircraft is in flight is known as the pressure differential. There is a limit pressure differential that an aircraft can withstand without sustaining damage to the fuselage or other components. Now, because of certain unwanted conditions that may develop, the pressurization system has relief valves, one positive and one negative. The positive pressure relief valves come into action when the aircraft's internal air pressure exceeds ambient pressure by a considerable amount. In this case, they discharge bleed air overboard to try and match ambient pressure. The negative pressure relief valves do the opposite. They vent bleed air into the airplane whenever ambient pressure is considerably higher than the aircraft's cabin pressure. This condition can occur during a rapid aircraft descent to low altitudes. As we talked about earlier, one forward and one aft outflow valve permit the discharge of air overboard in order to maintain the required cabin pressure. Both valves are identical, but one is obviously located in the rear and the other in the forward fuselage. Both valves are controlled with two separate channels, with backup power sources to provide system redundancy. The discharge of air is sequenced so that about 20% of air is bled from the forward outflow valve and the remaining 80% from the aft valve. This distribution improves cabin ventilation and smoke removal. In case of a single valve failure, the remaining valve can adequately maintain cabin altitude and full ventilation rates. Now, both outflow valves can be controlled automatically or manually. Automatic operation hardly requires any input from the pilots, except during pre-flight. Let's talk about each one, starting with automatic control. The ASCPCs supply automatic operation of the cabin pressure control system. To engage the automatic control mode, the outflow valve switches in the overhead pressurization panel must be pressed, obviously checking that the auto light is illuminated. In this scenario, the cabin altitude controllers design a pressurization schedule for the cabin. Maximum cabin altitude for the 777 is 8,000 feet, and if cabin altitude ever exceeds 11,000 feet, the cabin altitude controller closes both outflow valves completely to bring the cabin pressure back up to a normal value. The cabin pressurization schedule is based on a standard flight profile comprising the following flight phases: ground mode or takeoff mode, climb, cruise, descent, and landing mode. Let's talk about each case in particular, starting with the ground mode. On ground, the ASCPCs command the outflow valves to a full open position to ensure that the cabin does not pressurize whenever the aircraft is stationary or during taxi to the runway. At speeds above 25 knots, and once the pilots have commanded the engines to higher than 60% N1 for a few seconds, the ASCPCs understand a takeoff condition and do the following. They move the outflow valves to a slightly less open, more closed position. This pre-pressurizes the cabin to 0.1 psi above takeoff field pressure to avoid any uncomfortable pressure bumps for the passengers during rotation. Whenever the air-ground sensing system switches from ground to air, or when the aircraft climbs beyond 1,000 feet, the ASCPCs enter climb mode. When engaged, the climb mode calculates and sets a target cabin altitude during cruise, keeping the 8,000-foot limitation in mind. Cabin rate of climb is also calculated and limited to lesser than 500 feet per minute. Outflow valves are modulated to give a smooth change in cabin pressure. Another limitation you should keep in mind is that cabin to ambient pressure differential may not exceed 8.6 psi. The climb pressurization mode has two submodes, FMC climb and internal climb mode. Whenever FMC data is correct, the autopilot is engaged and VNAV is on. FMC climb mode takes priority. In this scenario, airplane cruise altitude, landing field elevation, and cabin limits are taken into account to design the pressurization schedule. When FMC climb is not engaged, internal climb takes place. In this mode, cruise altitude is set to 43,100 feet and target cabin altitude is set to 7,950 feet. If the takeoff was made from an airport higher than 8,000 feet, the cabin descends to the cabin cruise altitude while the aircraft is climbing. Now, once the climb is stopped and aircraft altitude does not change more than 100 feet for more than 3 minutes, the ASCPCs enter the cruise mode. At cruising altitude, the ASCPCs adjust the outflow valves to keep the cabin pressure constant at the value calculated for the cabin altitude target. As simple as that. When the aircraft starts descending and has descended at least 1,000 feet below cruise altitude, the ASCPCs command the descent mode. During the descent mode, the outflow valves gradually open to give a smooth change in cabin pressure. Target cabin altitude is set so that the cabin pressure value is slightly higher than landing field pressure. Similar to during climb, when the aircraft descends, the pressurization system also follows one of two logics, FMC descent or internal descent. During FMC descent, landing altitude data is used to design a descent pressurization schedule so that the cabin reaches its target cabin altitude when the aircraft reaches landing altitude. The normal FMC descent schedule provides a 300 foot per minute cabin altitude descent rate until a cabin altitude that is slightly lower than the landing altitude has been reached. This ensures a slightly positive cabin pressurization during touchdown. When FMC information is lacking, the pressurization logic during descent follows the internal descent mode, where the cabin pressure is changed at a maximum rate until either the target cabin altitude has been reached or the 8.6 psi pressure differential limit imposes a restriction for cabin pressurization. If the landing is planned at an airport above 8,000 feet, the descent schedule allows the cabin altitude to exceed the 8,000-foot limitation in order to match the field altitude. If for any reason the landing altitude data from the FMC becomes unavailable, the flight crew may select a landing altitude with a knob located in the pressurization overhead panel. However, this becomes part of the manual way of controlling cabin pressure. If no landing altitude data has been input by the flight crew, the system assumes 1,000 feet as a standard value. Lastly, when the aircraft lands, the ASCPCs command the outflow valves to fully open and depressurize the cabin at a rate of about 500 feet per minute. If 45 seconds have passed after touchdown and the outflow valves are not sensed fully open, the cabin commands a 2,000 feet per minute depressurization rate. In case of any significant system fault, or if it becomes imperative for safety reasons, the outflow valves may also be controlled manually. This would imply that the whole pressurization system would enter manual control. Cabin rate of change and cabin altitude may be controlled by modulating between open and closed the position of both outflow valves. The outflow valve manual switches allow this. If the switch is moved up to the open position, the related outflow valve is driven to move towards open, similar to when the switch is in the closed position. Intermediate valve positions can be selected. It does not have to either be fully open or fully closed. Whenever the manual mode is selected in either outflow valve, pressurization system indications automatically appear in the ICAS display, which leads us to the cockpit indications part of this lesson. Pressurization system indications include duct pressure, cabin altitude rate of change, outflow valve source of control, outflow valve position, cabin pressure differential, landing altitude selection, and landing altitude. Automatic display of the pressurization system indications occurs when either outflow valve switch is operating in manual mode, or when landing altitude is manual, cabin altitude is above a normal range, cabin pressure differential is above the normal range or is excessive, or pneumatic duct pressure is below normal range when the engine is running. This lesson covered all the main aspects of the air conditioning and pressurization systems aboard the 777. It's interesting to see that a considerable level of redundancy is built into both systems, with multiple controllers, channels, and a manual backup in case things go wrong. Here are a few key points to remember about air conditioning and pressurization. The CTCs set the packs to supply the coldest air necessary for the zone that needs the lowest mixed manifold temperature. Cabin zones that need a higher temperature receive mixed manifold air mixed with trim air. Recirculation fans help bring down the air demand over the pneumatic system and the packs by taking cabin air, running it through a series of physical and chemical filters, and then reinserting it back into the cabin. Packs are automatically shut down whenever there are significant system faults such as an over-temperature condition. Any one normally operating pack can adequately maintain cabin pressure. As aircraft altitude increases, ambient pressure decreases. Therefore, as cabin altitude increases, cabin pressure decreases. 20% of air is bled overboard from the forward outflow valve, and the remaining 80% from the aft outflow valve. Either outflow valve can adequately maintain the cabin pressurized. Outflow valves are normally operated automatically, following the typical flight profile. Manual control is achieved with cockpit switches. Remember, drive the outflow valve to closed if you need more air in the cabin. This will increase cabin air pressure therefore reduce cabin altitude. Vice versa when you drive the outflow valve to open. This lesson wraps up the air system section of the 777 groundwork. We hope you enjoyed it, and stay tuned for more sections. Until then, thanks for watching, and throttle on!